In this lecture segment and the following one, we'll look at the overall goals of software design before going into detail on design methods and language features. Software design has a number of goals, all related to managing the complexity of software, as emphasized in the prior topic on large software systems. The order of importance of these goals is somewhat subjective, and I'll list them here in roughly descending order of importance, at least from one viewpoint. The number one goal of software design is to organize large software into manageable pieces that fit within the keychain light of human memory and comprehension. The ability to abstract the other 99,000 lines of a million-line codebase while you work on one 1,000-line piece is essential. This is the central reason for all forms of functional and data abstraction, whether it's grouping code into functions, grouping data and functions into structures or classes, or grouping classes into packages. And those are all things that we'll look at in more detail when we cover language features for object-oriented design. If you put a 40-line piece of code into a function called compute_tax_due with clear parameters and return value, then you don't have to think about or understand those 40 lines unless you need to repair or modify that function in particular. If all the behavior for managing a tax return, including methods for computing the tax due and adding income and deductions, printing the form, etc., if they're all grouped along with the data for the tax return into a class, call it tax return, then unless you're working on that part of the code, you just know that a tax return object can manage tax returns and you don't worry about the details. Imagine, by contrast, what it would be like to work in Java if you had to know the inner details of a string object just to work with strings. If instead of writing str.to uppercase, you had to deal with the string's length, str.length, and its characters, str.data, you had to write a loop to capitalize the data and take into account all the complex capitalization rules that are associated with international Unicode values. To uppercase works in many languages, after all. It's not just that it would be error-prone and would break if the string fields changed in some future version of Java. It's also that you'd have to think about all that stuff when you want to work on the rest of the program. Now, at this point, let's introduce a term that we'll use throughout our design discussions, and that is complexity cost. And by this, we mean the mental burden placed on the developers, and in some cases the users of a program, due to the amount of detail, inconsistency, repetition, and sheer code volume of the program. Every program must incur some complexity cost, or it wouldn't exist in the first place. But reducing complexity cost is a major goal of good design. Now, this is, by the way, a course-specific term, though if you use it in industry, people will generally understand what you mean. Indeed, the term complexity cost comes up more often in management discussions, with the same basic meaning, but applied to human organizations rather than code. There is a near synonym that started appearing around 2009 and has rapidly gained widespread use, and that is technical debt. Now, this lacks the directness of complexity cost, and it sounds like a financial term, but you should know it as well, since it's more widely used. Another good metaphorical term, by the way, for this idea that you sometimes see is software entropy. Now, complexity cost and technical debt are among the most important concepts in this class, and close attention to these costs is the hallmark of experienced designers and of good designs. Now, it's hard to place an exact measure on complexity cost since it's a subjective measure of the mental effort necessary to comprehend and to modify a code base. Probably the best concrete measure would be to clock the time required by a new developer to comprehend the code well enough to work on it, but even that will vary per developer. Nonetheless, it can still be said that the complexity cost of two different designs for precisely the same program behavior may vary by a factor of 10. It's perfectly possible for the same program to be implemented following two different designs and with two differing degrees of coding discipline, and for the first version to require 10 times the effort to comprehend as the second. And of course, the point of good design is to arrive at the second version, not the first. A quote from Chris Gale, who's Vice President of Engineering for Yammer, sums this up pretty well. He says, "Among the most dangerously unconsidered costs is what I've been calling complexity cost. Complexity cost is the debt you accrue by complicating features or technology in order to solve problems. Sometimes complexity is a necessary cost, but only organizations that fully internalize the concept can hope to prevent runaway spending in this area." So moving on to the next goal, let's talk about communication about software. Another goal of design is to enable developers to communicate about different parts of the software using abstractions and metaphors that they collectively comprehend. Classes, modules, inheritance relationships, standard design patterns with names, they all form a language that we use to describe software organizations to one another. And there are visual patterns and terms that go with the verbal ones. Standard ways of drawing classes and their relationships, patterns of program logic, states of the data, etc., all allow developers to communicate with one another easily on whiteboards or paper. The UML standard for object-oriented design diagrams, which we'll study, is currently the most popular example of this. And interestingly, like other language-related matters, there is controversy as to the best way to communicate and draw ideas. And there is evolution of those ways of communication. In the 1970s, the state-of-the-art, at least outside academia, was structured programming. And that just means using nested if statements, loops, and so forth, instead of jumping wherever you like with go-to statements. And then modular programming grew in the 1980s, and then was followed by object-oriented design in the 1990s. In the first part of the 21st century, functional programming, as found in Lisp and in JavaScript and other scripting languages, that's taken the lead as the new design approach. Such programming is beyond the scope of this course, but you may encounter it in another course. At the risk of sounding deconstructionist, one might stretch a point and say that design is a cultural construct, an agreed-upon way of thinking about and organizing software systems. And like other cultural phenomena, design approaches vary generationally, and they evolve across the decades. Though unlike literary or clothing tastes, software design styles do exhibit general forward progress. Older design approaches, like structured code or data abstraction, are subsumed as a natural part of newer ones, like object-oriented design. And object-oriented design remains relevant even in the present era of functional programming. Now, in the next lecture segments, we'll look at three more goals of software design: modifiability, reusability, and testability.